Okay, good afternoon all. So thank you for registering for the course and for attending it. So I'm going to give you a short introduction. So move from these slides with the title and to a short welcome presentation. So here we are. So the course is called Computational Thermal Hydraulics using Code Saturne. So we are going to explain what the steps are to be able to run some simulation using Code Saturne. So a part of the course is run on a virtual machine or a local machine. And some tutorials, the last one from today is going to give you the chance to use ARCHER2, the UK national facility hosted by EPCC in Edinburgh. And you're going to run a simulation overnight and post-process the results tomorrow, and then run another tutorial with more feature of the code. So I'll first give you a very quick overview about what STFC is. We've got 3 tutors from STFC, Stefano Rolfo, Wei, Wang, and myself. And Juan Uribe is from EDF Energy. So he gave a short introduction to EDF and what they do and what they use Code Saturne for. We also have the support from EPCC and 3 persons. So Claire Barras, Juan Rodriguez Herrera, and William Lucas, who is going to help us mainly for the part devoted to ARCHER2. So STFC stands for the Science and Technology Facilities Council. So it's one of the councils of UKRI, which has been set a couple of years back now. And so we provide access to the major national and international scientific research facilities with about over 2,000 staff. And STFC operates 7 separate sites. The 3 of us, Wei, Stefano, and I, are located at the Daresbury Laboratory, which is Daresbury being between Manchester and Liverpool, just to give you an idea for people who might not be familiar with the UK geography. And so we also have other facilities like a telescope in Hawaii, which is probably a little bit more fancy than Daresbury. So concerning the course itself, here are the main features. So we are going to go step by step. You know, first working on the virtual machine or your local computer if you've got Code Saturne installed on it. So the idea is for you to get familiar to the graphical user interface. And for this course, we're going to run the same test case in different working conditions. So the test case is about a flow in a bundle of tubes. So that kind of flow, you can find this type of configuration in heat exchangers, for instance. So the first tutorial is about a laminar flow with different type of meshes. Then later in the afternoon, this is actually the highlight of this course, is to run an advanced turbulence modeling simulation based on large eddy simulation. And so these type of simulations are quite costly, but because of the power we get having access to ARCHER2, it's possible to run an overnight simulation and to be able to capture most of the feature of the flow. So tomorrow there's going to be some post-processing session to analyze a bit the results of the overnight simulation. And then another feature of the code is going to be looked at, which is based on internal coupling, and more physics going to be added to the case with large ND simulation and conjugate heat transfer. And finally, because we got access to a supercomputer, we are going to have a short tutorial about how to tune the code depending on the computer, depending on the configuration which is used. And so this is going to be the last tutorial before the end of the course. So I only mention here the tutors from who've got experience in Code Saturne. So that's Juan Uribe, myself, Stefano Rolfo, and Wei Wang. And as I said before, I mean, Claire Barras, William Lucas, and Juan Rodriguez Herrera are going to help us mainly for if we got problems setting up accounts or also to run on ARCHER2. So here's the agenda of the course. So, I mean, after this step, Juan Uribe is going to give a general introduction to Code Saturne. Then it's time for the first tutorial on the local or virtual machine. And after the coffee break, I'll give a short presentation about HPC for CFD mainly. And there's also a slide about describing how ARCHER2 works, just for a quick overview. And then for the rest of the day, you're going to work on the large AD simulation of the setup for a flow in tube bundles, hoping to submit a simulation overnight. So thanks to PRAISE, which is a partnership for advanced computing in Europe, and who's partially funding this course, we've got access to 20 nodes of ARCHER2, and each of the nodes having 128 cores. So it's possible to run this relatively large mesh overnight. So yeah, and tomorrow we'll post-process the results, and to get access to most of the feature or to all the features of Code Saturne, it's important to use user subroutines. So Juan Uribe is going to introduce these, and then we will add conjugate heat transfer to the large AD simulation and show you other feature of the software, which is able to interpolate a solution to a mesh of a different size, and then to restart from that simulation, so which allows to speed up some of the calculation. And after the coffee break, we will talk more about HPC optimization and influence of the partitioning to try to get the best of the machine we have access to. So I think I'm done here now. So have you got any questions at the moment? So the best is probably to raise the hand if you want. So if not, we're about to start the course, and I'm going to stop sharing the screen, and Juan is going to start the presentation on introducing Code Saturne.
Thank you, Charles. Hello, everybody. My name is Juan Uribe, as Charles said. I work for EDF Energy. I just sent a poll to make sure that you all have a working version of Code Saturne before we start the course. And hopefully, it seems like everybody has said yes, I think. Okay, good. Normally, we have these courses in person, so it's a shame we cannot see you and share with you. So we're gonna try this and see how it goes. Hope you can see the slides. If you have any questions or if you have any problems, feel free to either put something in the chat or raise your hand, and we'll try to deal with that. As I said, I work for EDF Energy, so I'm going to just give you an overview of EDF first, and then I'm going to introduce Code Saturne, which is the software we're going to use for this course. Give you the basic idea of how things work, and just basic steps for running a very simple case. And then we'll go through the tutorials, which are designed for you to do it on your own. So I'm not gonna do the tutorial with you. We're just here to we'll give you the material, and the idea is that you follow the steps that are in the tutorials, and we're here to help you with any problems that you might have. Next slide. So EDF Energy is part of the EDF group, which is an electricity company. It's half owned by the French state. EDF Energy is the UK name for the company. We have 8 nuclear power stations at the moment. 14 of those are gas reactors, and there's 1 water reactor. We also have wind farms, and we've just closed the coal station that we had, and we still have a gas station at the moment. We're building 2 new reactors in Hinkley Point that should be coming online just as the old gas reactors are being switched off. So we have a series of problems in our business. One of them obviously being heat transfer and fluid flow, and that's where we develop tools like computational fluid dynamics codes to tackle all of our problems. As I said before, we're part of the EDF group, which is a much bigger entity than EDF Energy. Here are some figures that are not really updated very recently, but we do have in the UK, we have a research and development center, which has 4 teams. I'm part of the low carbon generation team, which does modeling and simulation for our nuclear power plants. But we also have all sorts of research activities from the generation part and also from the customer side of the business. So things like smart grids and smart meters and things like that. One of our main advantages of being here in the UK is that we have a very good set of partners. We work with very different universities and research centers and companies that share interest in the same problems that we have. One of them being the Science and Technology Facilities Council, when Charles and Stefano work. So we have a very strong collaboration with them, and we also have a very strong collaboration with the University of Manchester, where I am based, actually, in a joint research center with them. So that's a very quick overview of EDF and the company. As I said before, we have a series of tools computational to develop to solve all the problems that we have in different parts of the business. Code Saturne is one of them. It's a three-dimensional unstructured finite volume code for computational fluid dynamics. It's open source, as you probably know, because you all seem to have it already working. So you can download it and use it, modify it, and do anything you want with it. You can see all the source files and find out how everything is done in it. It's a single-phase code. Has very different types of turbulence models. It also has a series of modules, such as compressible combustions, electric arcs, and conjugate heat transfer that we'll be using later on in the course. And many other modules are being added as they're required. The code is mainly written in C. Half of it is C. It's about 37% of it Fortran, and a little bit in Python. Originally, the code was written all in Fortran, and then it has been moving towards C very slowly in the past 20 years. And we use Python mostly for the graphical interface and for the file manipulation. You will see that later during the tutorial. It has a graphical user interface. It uses Qt and uses an XML input file. We'll go through that later. It's highly parallel. It uses APA and OpenMP as well. One of the main advantages is that it's highly validated. As you can imagine, for the nuclear industry, we are required to be very strict in validation for the nuclear regulators. So they ask us to have a very strong validation verification suite, which is it's run every time that something is changed in the code. It's highly portable. You can pretty much install it almost anywhere, provided that you fulfill the prerequisites in any of these operating systems. And we've tested it in many architectures, including the Cray system that you'll use later on today. We have here a description of the different parts of the code. We have a graphical interface, which you will be using to create an input file, basically. You have a preprocessor, which will read a mesh. Code Saturne doesn't have a meshing software, but it can read a very wide range of mesh formats. Once you have supply a mesh to the code, it goes through the preprocessor and create what is an intermediate mesh structure. That's an internal file in which this mesh has been transformed into all the information that Saturne requires, like phase centers and normal vectors and connectivity and things like that are not necessarily present in all the mesh formats. So once that translation is done, everything is passed to the kernel, which is basically when the bulk of the calculation takes place. It solves the equation that you are trying to solve, and it creates an output. Code Saturne doesn't have a post-processing utility either. It just relies on writing files that can be read by other post-processing software. We will be using ParaView, which is also open source visualization software. So the graphical interface is it's a very simple thing, really. It's supposed to guide you through the different pages. You can see in this picture on the left-hand side, all of these titles refer to a page where you would go in and select values or input values for the different things that you need to do during the setup. Anybody that is familiar with computational fluid dynamics know that there's a lot of different options that you can choose. So in that sense, it's not very different to any other computational fluid dynamic software. At the end, when you finish doing all of that, you will save the file. File will be taken as an input for the calculation. It has a very basic mathematical expression interpreter, in which you can introduce formulas for things like density as a function of temperature, for example, or some formulas for boundary conditions, something like that. Not everything is available on the graphical interface. There's a lot of things that are only accessible by subroutines. So for us working with the subroutines, the use of subroutines or use of functions is very common. This is a very normal thing to do, and we'll go through those tomorrow. So there's a command called Code Saturne that once you install the software, you will have access to this command, and that's the one that pretty much allows you to do anything related to Code Saturne. It can start the graphical interface, it can run the code, it can do the compilation, it can create your environment, your files. It can give you information about your installation. And it also has what we call a study manager, which is what we use for the validation and verification, which allows you to run a large set of cases almost automatically. The first thing that you need to know is how to get information and help, obviously. So if you tap minus help for each of the commands in the previous slides, you get the help for that particular command. So in this case, in this example, if you type Code Saturne info -- help, it will show you what options do you have for the information subcommand, which means that you can either select what type of guide you want, or you can define a PDF reader, or you can just print the version number of the code that you're using. So for example, Code Saturne info -g user will bring the user manual. You can have the user manual, the installation manual, some developer's guide, and auto validation and verification as well.
Hi, Juan. I don't think we can hear
can also be accessed from the graphical interface. If it's installed correctly, you will get the same PDF files as displayed here. There's an email support for all things related to Code Saturne from EDF, but obviously the support is given without any warranty, as there's no contractual agreement to do that. But there's a big forum in the website where you can find a lot of answers to most common problems, or you can contact the development team directly there, and they'll give you the solution to whatever problem you may have. So I mentioned before, there's no mesh generator in Code Saturne. EDF has its own open source platform called Salome, which has a CAD and a mesh generator and a post-processing software. Code Saturne can be installed within Salome, but that's an extra procedure that is not generally done. But there are also many other types of mesh files that we can read. Some of them are here, and we can read files from CGNS, for example, which is a very generic format that most of the mesh generators can export into. Med file is a particular format developed by EDF as well, that is using the Salome platform. And we can also read CCM files, provided that you get a library from Siemens. So, as I said before, when you have a mesh, there's a pre-processing stage that is done by the code that is independent from the main kernel. You can run this separately without the needing to run the whole code. So you can just check your mesh before you start going through your calculation. It will check that the mesh is valid. It will include the periodic boundaries if you set them up. It will show you what boundaries have been defined in the mesh file, and you can run a quality criteria set up so that it will tell you things like were the mesh highly distorted, or whether are warp faces, or if there are any negative volumes, things like that. And then you can see all those results in parallel directly before starting your calculation. In terms of how to run a case, it's a bit more different than from other software. And Saturne expects to find by default a specific folder structure where it organizes all the files and all of the input files and of the user subroutines. So we don't just, because I was explaining, you have different input files and different. The easiest way to do this is to use the Code Saturne command to create this structure. It's based on basically what we call an study case hierarchy, in which you have a folder which you can name your study. Say, for example, you're doing a pipe flow, then your study name would be pipe, and inside each study you have different cases. You can have different boundary conditions, for example, or you can have different turbulence models or different meshes. So each one of those would be a different case. So to create a case, you can type this command, create, Code Saturne create, -s will create a study, and -c will create a case. You can also create cases after you've created the study. You can also use -c, create another case, and it will just create a new folder. So it basically looks like this. So imagine that you have your first study, your first case. When you create this study, you have a mesh folder. When Saturne will look by default there to find any meshes that you have for the computation, and it has a post-processing folder for you to do any scripts that you want to do for post-processing, for example. Then the case file folder will be created with this structure here that you see in the picture. You have data, resu, scripts, and SRC folders. The data folder has a script that will run the graphical interface. That's the equivalent of typing Code Saturne GUI. And it also has some reference files where you can find things like thermal properties, databases, and things like that. In the result file is where you're going to have the results after you've run a computation. So at the beginning is an empty directory. But every time that you run any computation, the results will be stored there by default. The script directory has a file called run case, which is basically the equivalent of clicking run on the graphical interface. We'll go through why is that later in the session when we go to the remote machine. You'll see why that is an advantage. And finally, the SRC folder is where we're going to put all the subroutines that you want to modify. It has some examples for things that you can do with the subroutines. We'll go through that later as well. So the basic steps for running a case using the graphical interface is first to, after you've created this study case structure, you will go to the data directory and type GUI. You will bring out the graphical interface, which looks like this. Then you just click on have this logo at the beginning and an empty space. So when you create a new case, the new file button, it will give you a series of pages where you need to fill all the things that are required for a computation. So most of the things have a default value. It's up to the user to make sure that they are changed to whatever case is necessary. Obviously, the boundary conditions at the beginning are empty, so there's no default boundary conditions. Case won't run until you put some boundary conditions and some mesh file. And most of the pages have a default value. So once you go through all of those pages, you can save the file. By default, if you just click save, it's going to be called setup.xml, and it's going to be saved in data. And then you have this cogwheel play button, which is basically run. That would bring up this window in which you can set the number of processes that you want and the number of threads if you have compiled this with OpenMP. So you can just click run calculation button. And once you do that, there will be another new window that gives you some details about what's happening. So it will tell you which version of the code you're using and where is that version installed in your system. And it will tell you where your results are going to be. And then it will start printing things as the calculation goes along. So first step, if you have any subroutines, it will compile and link those subroutines. Then it will copy all the necessary files, including the mesh and the input data. Then it will call the preprocessor stage, which would read the mesh file. And once all that is done, it will start the calculation. And then at the end, it will just tell you that it's done some post-calculation operations and finish. And you have some buttons at the top this window that allows you to stop the calculation or kill it, and also a convergence tool. As I said before, not all the modules are available on the graphical interface, so sometimes you need to use Fortran or C files for changing things that you may want to use. So the convergence tool, when you click here, it will show you basically by default, it will show you a plot of the residuals of the equations that you're solving. And if you set up monitoring points, so these are points that you select on the domain where you want to see the evolution of the variables, you can plot those to as the calculation goes along. So that's very convenient for knowing how things are behaving. So sometimes you need to use Fortran files or user subroutines. They could be also in C as well. And in fact, you don't need to use the graphical interface at all. You can run a complete calculation only using the user subroutines. So obviously, you need to be much more comfortable knowing the subroutines than the graphical interface, but it is possible. If you want to do that, you can find in the SRC folder examples and reference files. So the reference file directory will have empty files, and the examples will have the same files, but with some examples that you can use to take inspiration, let's say, or copy paste from there to whatever you want to do. If you don't want to use the graphical interface, you need to have at least two different subroutines, the CS user parameters file and the CS user boundary conditions file. So you need to, in your CS user parameter files, you will define things like physical properties and numerical parameters like your time step and your number of time steps. And then in your boundary conditions, you need to define the boundaries that will match the mesh that you're using for this case. One thing that is important to know is that if you have the same value set up both in a subroutine and in a graphical interface, the value that you set up in a user subroutine will have precedence over the graphical interface. So if you have a value for the density in the graphical interface that is different from the one in the user subroutine, the one that you will be using will be the one in the user subroutine. So if you're not using graphical interface, you will also need to use CS user script Python file that would tell the code where to find the mesh file and where to do other things that are optional, such as find a restart file or do some sort of post-processing code, things like that. That can be found in the data directory in the reference, and we need it if you don't use the graphical interface. The tutorials that we're gonna do, we're not gonna be using this, as we're gonna create an XML file, even though we're gonna use some subroutines later. Once you have set up everything in your data directory and your subroutines directory, you can go to the scripts directory and type run case. As I said, this is the equivalent of clicking on the graphical interface, the run button. So if you don't have the graphical interface, that's how you start the case. So what happens after you start running is the same thing that in your terminal, you will have the same stages that I showed you before on the graphical interface window. It will give you the location of the code, the location of your results, and it will show you at which stage of the calculation you are. One thing that is particular for Code Saturne is that the results file, that every time that you run the calculation, you will create a new directory. So that line there is always going to change with the date and the time of your run. So it won't overwrite a previous run. But that is the amount of files that you create are quite significant when you start running several instances. Once you go to that results file, you'll see that you have various files in there. The listing file is one of the main files. There is a text file that contains a lot of information on the values of that the code is obtaining through the solving of the equations at each iteration. So it gives you maximum and minimum, and give you the number of iterations that it did for each variable, for example, and what level of convergence was reached. It will tell you some things like if there are some clippings done or things like that. Your setup log will contain a lot of information about your case before it starts to run. So it will tell you things like what type of gradient calculation you've chosen for each variable and how many variables you have, etc. So you'll get also things like your post-processing results to see the paraview files, etc. So one important thing is what to do when you have problems. First thing that can happen is that you have a compilation error. So you'll see a message similar to this when you have a compilation error, compile or link error, and you will see that it tells you that what the error if you look at the compile.log file. Then if the compilation goes right, then the next stage is the preprocessing. You could have an error there as well. See, for example, if your mesh is found to have negative volumes, or the mesh file is corrupt or something like that, you will find it in this preprocessor log file. And if that goes all right, then your calculation could also have problems. In that case, you would check the listing file, and any error files, it would tell you the things like, for example, if your equations are not converging, or if your boundary conditions are wrong, or things that can happen, or if something didn't work, it would appear there. So when everything goes all right, as I said before, your results would be in a directory that will have the date where it started. So you have the year, the month, the date, the hour, and the minute. And inside you will have the post-processing folder, which is what you can use to see the results and create things like contours, vectors, plots, or extract profiles, things like that. And if you set up monitoring points, you will have a copy of those values in the monitoring points, sometimes called probes in Code Saturne language. The checkpoint directory is quite important because that has all the values at all the cells for the last iteration stored. So you can from there if you want. That's a file that is only readable by Saturne, so it's binary file. You will have a SRC folder where you have all the copies of all the subroutines that you use, and you will also have a copy of any output that you define. So, for example, if you define files or you define data files at a certain location, and of course you will have all the logs for all the stages of the run, as I said before. You will also save a copy of the XML file, which is your input file generated by the graphical interface. So, in summary, this file with the date, this folder with the date, will have basically a copy of all things that you used to run that case. So you can rerun it again if you want, but all the information is there. So the post-processing folder will have a series of files. It will have this by default are in format for Insight. Insight is a visualization software. Is not open source. There's a free version that is up to, I think, 2 million cells. But if you want to do more things with that, you need to pay for that. But ParaView, which is an open source and free software, can read these files directly. So that's why we haven't changed them, basically. The case file is the one that you would load in ParaView, and that will tell the software what to read, what variables are there, how many time steps, what's the geometry. So all of this information is split over several files. And you can change how often these results file are written. So by default, you would only write it at the end of the calculation, but you can change that if you want to see, for example, some animations, or you want to save different stages of the simulation. One important thing here is that you can also create parts, and we call parts is subdomains, where you can select a smaller set of cells where you're interested in. So if your mesh is very big, your post-processing file is going to be very big because it has all the geometry file, all the geometry information in there. And sometimes you don't want to see the whole thing, or you don't want to copy a very big file. You can create subsets of those parts of the geometry where you're interested. And those subsets can be either geometrically defined, say, for example, all the cells that are lower than x equals 0, for example, or they can be based on functions. So you can say all the cells that have a temperature larger than 20 degrees, for example, or things like that. So it's quite useful to when you have very large cases and you don't want to see everything. This is an example of what you would see in ParaView. So in ParaView, you will load your Insight files, and then you can do these things. Color the domain by any of the variables, create the streamlines, show the mesh, or hide the mesh, or anything like that. You also get a folder with the monitoring points, as I said before. You can define which variables you want to monitor. By default, when you create a monitoring point, you would assume that you want to monitor all the variables for that point. And then there's a file for each variable. That file has a series of columns, and each column is one point. So it could be a comma-separated value or a space-separated value, .dat file. And it will show you the variation of that variable along the number of iterations or time. And you can select how often that is saved. So by default, it's every iteration, but you can do it every 10 iterations or everything. And at the end, it's just a text file, so you can open that with Nuplot or Grace or Excel or any other program. So that's an example of what you would see for monitoring points that have one value and then converge to or don't converge to a final solution. Okay. So that's the first introduction. Are there any questions from anybody? Well, I hope you could hear me okay and see the slides okay. So what we're gonna do is go through the first tutorial. And I'm gonna show it here. You should have a copy of this with the files that I sent you. I'm gonna share my my screen. Is anybody here using a virtual machine that we sent, or your own installation? Complete silence. Okay. If you have your own installation, downloaded the tutorial files zip file in which you can find a copy of these PDFs. If you have the virtual machine there on your desktop, and you can just start with the Lamina one. If anybody has any problem using the virtual machine or starting Code Saturne, please let us know. I'm gonna put up the first tutorial here. Give me 1 second. All right. So this is the PDF that you should all have. And the idea now is that you go through this tutorial. It explains a very, very simple case to start with. See if I can make this bigger here. Which is, as Charles mentioned at the beginning, this is a tube bundle. So we start from the most basic domain, which is just what is dotted here in this picture. And we're going to just do a very simple laminar flow. You can run it either on your PC or in the virtual machine. The meshes that we are providing you are very, very small, so it's not going to be very heavy on your computing resources. And it's going to run fairly fast. We only do a few iterations, so it's just for you to learn how to create a case and run it. So please feel free to go to the pages of your tutorial and try to run the same case with different meshes. So this is a step-by-step, so it should show you all the details using the graph interface, of course. If you have any problems, feel free to ask. Either type something in the chat or just raise your hand and talk. We're happy to hear you. Some of these explanations are already covered in the presentation that I gave before. You'll see that by the end of following these instructions, you should be able to run your first Saturn case. Okay. So and we're here if you need us.
Okay, I think we are back to the break, from the break, sorry. We are going to have a presentation now about HPC and HPC for CFD with how it is managed into Code Saturne. So I'm going to load some files and share them with you. Can you see the slides?
Yes.
Yes.
Okay, thanks. Okay, so this presentation is for about half an hour or so. So this is to show the capability of Code Saturne using many processors. But you have also to think that the code has been written for massively parallel machines, but it also run fine on just one processor without MPI and just without a bare compiler. So sorry. So basically, the motivation of these talks is that the current generation of machine are operating at petascale, and exascale should be ready by the end of this year or maybe next year. So if you see that petascale correspond to about 2 to the power 50 floating point operation per second, so which is massive. So what do we do when you are doing CFD and we've got access to a full machine like this? There are several options. So it's possible to increase the size, the computational size of the current configuration. So you can also increase the Reynolds number, make it more complex, adding more physics, or also operating at different scales. But it's also possible to do some sensitivity analysis, so running parallel simulation who actually don't communicate with each other. But at the end of the simulation, you basically extract some feature through statistical analysis. So we find that there are, there are basically two different approaches, so either the mesh-based methods or the meshless methods, but they've got a lot of common grounds. So we try to identify some of them, and we try to see what's done in Code Saturne to run at extremely large scale. So we identified 5 different issues you could hit running a CFD on this large machine. So the first problem is the mesh generation. So usually a mesh generator are serial. So you need a very, very fat node if you think that you want to generate a mesh using billion of cells. So I mean, are there ways around? So we are just going to see what can be done into the code for that. Then when you got your mesh, you need to distribute it across the cores or the nodes you've got access to, but you need to do it in an efficient way, especially if you need to repartition in the course of the simulation. Then solving the PDEs is also obviously key, and this is an aspect which has been focused on, and with a lot of improvement along the years. Then obviously the big machine that works with queuing systems, so the chance that you have to run only a chunk of your simulation given the 12 or 24 hours you've got access to is massive. So you need to have a process to down the disk and to read them very, very quickly. And we need to see if there are bottlenecks in there. And finally, the MPIO, which has been developed for quite a while now and working well on terascale machine, is that suitable for petascale and now in the future for exascale? So we don't know that yet for exascale, but we kind of have an idea about what happened at petascale. So this is the content of the talk. So I'll pass to what is called the link pack performance. So some of you might know that there's a top 500 listing the 500 public machines, the fastest ones in the world. And there's a suite of tests which is run to assess their performance. So there's their theoretical peak, the theoretical peak of the machine when it's built, and then this lean pack suite is run to assess the maximum peak they really achieve. And so if you look at this over the years, so this go until 2019, but the slope is, the same trend is observed for the fastest machine, the basic, but also for the slowest machine of the top 500, which actually almost reach petascale. So that means, looking at this graph, that is very important to have a massively parallel code for CFD and to get the best of these machines. So the top 3 machines in November 2020, the trend to go for exascale now until a couple of years back was to add GPUs to CPU, or several GPUs or accelerators per node. But it happened that the fastest computer in the world doesn't use accelerators, but only CPUs based on ARM processors. But the common trend of all these big machines, the 3 first machines, is the number of core you've got on this machine. So they're all over 1 million. And the second and the third are 2 IBM power machines, and they all have accelerators. Summit's got 6 GPUs per node, and I suspect that CR's got 4 only. but 4 is already a lot of GPUs per node. And the last machine at the bottom is an old type of machine called Blue Gene, and which is decommissioned now. But this is where we run the largest test cases or tests using Code Saturne. This machine has got 0.7 million cores. So there's a requirement to build this machine. Basically, it's possible to run an exascale machine, to build an exascale machine at the moment, but one of the requirements is to limit the power. So until a few years back, the limitation of the power was about 20 megawatts, which is about 5% of what produces a typical nuclear reactor. So that's quite a lot. And the Fugaku supercomputer goes up to 30 megawatts. Is in Japan, by the way. So here the architecture which has been tested. So on the left-hand side, you've got the blue genes. So this were, as said, for the largest simulation been run on this. But the extensive tests have been carried out on Archer, which has been decommissioned, and some tests now are ongoing on ARCHER2, so the new machine. So these both are crays, but with different types of processors. So I wanted also to recall a bit what praise is, because praise has helped to develop some part of the code, and is also the praise that sponsor this course. So it gathers a good most of the European members, and so it's an international non-profit association, and it runs since 2010. But actually, it started in 2007, 2008 already. So at Asbury, we've been involved in a benchmark suite where Code Saturne is. So there's basically a suite of software that people can download to test their new computer, or test the performance of their computer and their new clusters. So in this suite of software, you've got 14 software, and Code Saturne is one of them. And there are only 2 of them dedicated to mechanical engineering, and the second one being ALIA, which is developed by Barcelona Supercomputing Center. And so at Asbury, we are actively involved in maintaining the presence of Code Saturne in this benchmark suite. So concerning the feature of Saturne, Rohan already showed that. So before, so what's important for this talk is that it's a mixture of the code is a mixture of C and Fortran with some Python to manage the simulation. So concerning the physical modeling, it always expands to get to more realistic physics, and it's driven because the EDF on its own has got to be able to simulate a lot of part of the nuclear power plant, and is driven towards massively parallel implementation, because in the future they expect to be able to simulate a full nuclear reactor. So you can imagine that, I mean, you will need a billion or hundreds of billion of cells just to run one simulation with advanced modeling. So the tool chain that I have here is very similar to the one that Rohan showed this morning. So you have to think that on the left-hand side, so just under the GUI, all this part is serial, and the kernel, which is on the right-hand side, all these paths is massively parallel. So now if we go to mesh generation, is that if you would use a technique called finite difference modeling, the meshes can be generated on the fly because the complexity comes from how the equations are solved, but not from the mesh generation in this case. When you go to finite volume, which is the case of Code Saturne, and you got cells or elements, I've got any type of shapes, you get very, very complex, in terms of structure, very complex meshes. And we are thinking now, in this case, are going towards a billion and hundreds of billions of cells. So it's impossible to do that on a serial machine, and because the memory is not available, and on top of that, it would take too much time. So there are ways around. So one way around is to build several parts of the meshes or the mesh independently, and to glue them, to load them into the code, and to glue them on the fly. So it's called mesh joining in Saturne. So this is used extensively. It was actually used to build the periodic boundary condition you had to build in the first tutorial. So this is the same technique. So basically, it's possible to glue conformal meshes, but also non-conformal meshes. So which is described in the bottom left in a plot. You know, when you can see an overlap of two different meshes, and extra faces are built there so that the interface actually becomes a fluid interface and not a binary interface. So this is done on the fly and fully parallel. So the other technique to generate massive meshes is to start from meshes that we can manage. So meshes we can manage can go up to, let's say, 25 to 40 million, and really up to 100 million with a massive stretch. And then the idea is to use a technique called mesh multiplication. So you would refine globally all the cells of the mesh. So a cube would be split in 8 cubes. A pyramid in, I think, it's 12 small pyramids. A tetrahedral, in 8 tetras, and a prism against in 8. And this is done on the fly. This can be done locally per processor, and is extremely fast. And by doing so, you actually multiply the size of your existing mesh by 8 once, and 64, and so forth. And you can generate massive meshes doing so. And you keep everything in the memory. You don't have to dump that on the disk. So you save a lot of time in terms of IOs. So in terms of performance, so the largest mesh has been run to date using Code Saturne has got 105 billion cells. So the simulation were run on Mira in Argonne in the US. It was a machine run by the Department of Energy over there. And remember, the machine had got 0.7 million cores. So for the mesh generation, we run up to 1/3 and 2/3 of the machine, and it only takes. It was taking 8 seconds to run 4 levels of refinement there. So it's extremely fast. If you imagine comparing to copying a file across, which is nearly impossible, and then reading and writing on the disks. They add the timing a little bit later to show the size. This is extremely fast, and it's only correspond to 1 time steps in terms of simulation, which is nothing. So then for a 13 billion cell mesh, we got timing. Actually, I mean, we've been tested up to the full machine, half of the full, the full machine, but using some hyper-threading, and so that as well is quite fast. So now that we got the mesh, we need to distribute this over the processors. So there are two main techniques. There are a very intuitive one, which is geometry based. So I mean, I'll explain a little bit later how it works. And the second one is a graph based. So you basically extract the graph of the mesh, and what you want to do is that you want to actually distribute evenly the load per processor, but you want also to reduce the communication between processors, because this communication can also really damage the performance of the simulation. So going further, one of the geometry partitioning technique used is based on space filling curves. So here you could see 2D examples. So starting from 2 squares, what you want a mapping between the 2D of the corresponding to the squares into 1D. So basically this line, Morton and Hilbert, are 1D line. It's just a very long array. And if you have 16 processors, you just chop equally or evenly this line. And each processor is going to run a chunk of this of these arrays. So tomorrow we're going to test different these two approaches for the tube model test case, and you would be able to compare the timings. And what usually affects the timings, the communication between processors. So this is for the geometry partitioning. In real life, it looks a little bit like this. The colors correspond to the index of the processors. So it goes from blue, which is 0, I guess, to red, which is the maximum number of processors. And you can see the Morton shape, which is called also Z shape, and the Hilbert shape on the right-hand side. So now, I don't detail here given any more detail about the graph-based approaches, but you can see that on the left-hand side, the top left-hand side, PtScotch, which is a solver, a library which allows to partition using graph-based techniques. So you can see the example on the 32 ranks or MPI task or cores, and the example compared to for Hilbert. So you can see that the shape of the subdomains are a little bit different. But now, if you use what is called a naive numbering without any of this treatment, you end up at the bottom of the slide with all the color all over the place. So basically, all the red at the bottom correspond to what is run on one processor. So you can imagine, it looks like, I mean, in that situation, all the processors are going to talk to each other. So this is going to very slow down the simulation. So the two first technique at the top, I mean, are to be chosen if you want to get good performance out of the machine on the code. So now, if we go to solving the PDEs, is that I mean, in CFD you've got two classes mainly, that the time explicit and the time implicit. So there shouldn't be any problem to run time explicit simulation at exascale, and basically to get good performance out of it, because the data, I mean, when you compute a kernel, the data are very localized. When you go for time implicit, you end up solving matrices, and then in the case of CFD, the matrices are very, very sparse, so you don't get much out of the performance of the machine, and you depend a lot on global communication. So in Saturn, a few years back, about 60% of the time were spent in computing the pressure. Now, I mean, because there have been a lot of improvements developing a multi-grid method, this is probably down to 30%, and the velocity is a little bit more costly now because it's all computed implicit. So you've got a block matrix with UVW there. And another part which is quite costly in solving the equation corresponds to what is called gradient reconstruction, when you got cells which are very, very skewed in the mesh. So, but if we tested the code on different machines, in this case they are blue jeans, and they've been tested up to the full machine. Basically, on the left-hand side, that shows the time to solution, which and the dashed line correspond to the ideal time to solution, and you can see that the slope is nearly the same, and you get a very, very good speed up. Now, if you look at the largest mesh with 105 billion cells, you also got a very good speed up in the solver. You know, the time spent in the solver. I mean, if you go from the first line 260,000 multiplied by 4 to 524 multiplied by 4, you got a speed up of 2, and from the first column to the third one, you got a speed up about 1.90 no, yeah, 2.90, so almost 3, which is to be expected. So the solver scales very, very well. And for 4 times, I mean, 8,000 is about 3 million. So that's the highest number of MPI tasks or cores that the code's been tested on. And that was already a few years back. Now, I don't have the results on ARCHER2 because the machine is not fully installed yet, and we would like to have the results on the full machine. But I mean, this is a comparison between Archer, which was just decommissioned, and the machine before, and we were going 2 to 3 times faster. Now on ARCHER2, we run up to 3264 nodes, 256 nodes, and we could see that comparing to 256 nodes on Archer, we were going about 4 times faster, which is very good. And the time to solution has got the same pattern as this one. But I mean, in a few months we get the similar plots comparing Hector, Archer, and ARCHER2. So, I mean, performance is important, but accuracy is also very important. So the technique used in Code Saturne is called finite volume, and the best can be achieved with a second order in space and time. So there's a test case called the Taylor-Green vortex test case, and some simulations have been run there up to 2,000 cube, so it's about 8 billion cells, and that's what is needed to recover spectral accuracy. So that's on the maximum on the right hand side, and this is also expected given the best order of accuracy we can get on Code Saturne. But I mean, if you want to run simulation which are only with hexaedral cells and in a box, Code Saturne might not be the best software to use. You should use a DNS software with a much higher accuracy. Now, if you are going for more complex geometries that will flow between tube bundles, Saturne is a good one. and retain this second order accuracy in space and time. So now another issue is that the architecture of the computers evolve all the time. So, but a trend which is common to all this architecture is that it increases the number of cores per node. At the point that a few years back, when you were bidding for time, you were asked for the number of cores you were using and you were paying on that. Now you pay for the number of nodes you're using, because the nodes can contain CPUs, accelerators, only CPUs, a mix of both, or GPUs. So, but for instance, on ARCHER2, you've got 128 cores on per node, which is sufficient to run the relatively large simulation you are going to run later. And it's also the same on other architectures from other vendors. And the trend is also to have quite a lot of RAM. But so you need to prepare the code for this architecture, but also things that you need to prepare it for accelerators. So in Saturne, there are some effort to put on GPU accelerators. So a few years back, a colleague from IBM ported a good chunk of the code there, and for the solvers. And what is being worked on is accelerating the gradient reconstruction, as I mentioned before. So these are some results which were obtained on Summit. So that was the second machine listed in the top 3 machine. And the code was tested up to 512 nodes of the machine. So you multiply by 6 to get the number of GPU which were used. So it's about 3,000 GPUs, which was quite a lot. And the comparison between CPU and GPU was giving a speed up about between 2 to 3, which is in the range of the other application being run on this software, on this machine. So now come the tricky bits, because usually a lot of time is invested in developing software and optimizing software, and a little bit less in iOS. But if we think about meshes of having billion of cells, I mean, you easily end up with 10 to 20 terabytes of data. So, which is probably impossible to move around, basically. So basically, in Code Saturne, we've got several post-processing aspects. First, the monitoring points on the probes. So you've been using that in the first tutorial, I think. Then you would like to be able to generate films with your data. And for public engagement, for instance. So it's very difficult to dump all the data on the disk, especially if you need about 1,000 to 2,000 or 10,000 instances. So the idea is to generate the frames either on a cursor grid and download and dump that on the disk, or to present some results on the fly. So Code Saturne is linked to a library called Catalyst, which is also part of PowerView. And it's possible to dump PNG files, which are very small compared to a full post-processing file. And then these PNG files are all just gathered and generated film. So maybe tomorrow, if we have time, I can show you a video that we've been building. And so this were run on an Archer to 98,000 processors and doing the plots only on the fly. So unfortunately, there's a massive bottleneck, which is the restart or the checkpoint process. because there's no other way that we know than dumping the full information onto the disk. And if we would dump only a part of it, when we would restart the simulation, we would have a transient time, and we would actually lose all the benefit of saving less data. So we really need to dump that on the disk. So in terms of IO and performance, so I mentioned that we ran some tests on using the 105 billion cell mesh. So the mesh size was about 20 terabytes. And the checkpoint files, there are two in Saturne. So the main one corresponds to UVWP, and the second one usually with the extra physics. So the simulation were run on 250,000 and 500,000 MPI tasks, and dumping the mesh was taking about, I think it's about 40 minutes. And if you remember that mesh multiplication was only 8 seconds, you can easily see that it's better to keep everything on the fly. But in there, I mean, that was just an exercise to write the mesh on the disk. And for the checkpoint, I mean, this is compulsory. So it takes 11 to basically about 25 minutes in total. So I mean, and this has been run also on tested on the full machine using 32 ranks per node in the case of the 13 billion cells. But okay, this is difficult, but this is doable. Let's put it that way. So in summary, just want to say that for mesh generation, partitioning tools, solving PDEs, and we've got tools in the code that can be used and have been used at a very, very large scale. So this 100 billion test case, I think in normal production runs are about a max between 100 million to 500 million, really. So the code is ready to run much larger simulation. For the best performance, depending on the machine architecture, so this is ongoing, obviously, because new architectures are always coming up. There's also an issue when you go to GPUs, is that each vendor get their own modeling, programming tool for that. So AMD's got a different one than NVIDIA and Intel as well. So we need to adapt the code in a way that it gets portable. So you might lose some of the all the gain. You might lose a little bit of performance if you use a more general tool, but these are options which are actually very, very difficult to predict and to account for. So at that time, OpenMP 4.5 and maybe 5 look like a good option for GPUs, but OpenSCC is another one. So we don't know yet in which direction it's going to go. And for the IOs, so they work fine on a GPFS system. So the IO system Lustre, which is used on ARCHER2, has been tested as well, and it works fine. But it requires a little bit more some settings, working on striping when you write do it from the disk. And really, the main bottlenecks is a restart on checkpointing files, but this is not only for Code Saturne; it's for all the CFD codes. And finally, I wanted just to show a very simplified sketch of how ARCHER2 works. So on the right-hand side, you get the features. So this is copied from the ARCHER2 website. So this corresponds to the machine when it's going to be a full capacity. So now, if I'm correct, you get about a 1/5 or 1/6 of the machine. So you got 4 cabinets instead of the 23, which are going to be completely installed. So this makes a machine which is already very, very quick, but is going to be reaching, I think, 28 petaflops maximum, which is going to give them a very good rank in the top 500 of the supercomputer. So basically, when you log on the machine, you go for the logging nodes, and from the logging nodes, you got access to the home, to the work directory. So what we have done is that we have created what is called a soft link here under the home directory so that you can use the work directory, but be aware that you cannot submit simulation or jobs if you are not in the work directory. So be sure that you run all the simulation from the work directory when you log on ARCHER2. And from the work directory, there's there's access to the compute nodes, so you don't see them. So this is hidden through the queuing system and the submission system, basically. But the simulation are run in parallel on the compute node. So in your case, it's going to be on one node, and which is going to have 128 MPI tasks. And at the end of the simulation, you recover all your results still under the work directory. So that's it for me. So if you have any questions, just please don't hesitate or write them in the chat, and I can answer while you are going for the next tutorial, I guess. Thank you.
Feel free to speak and just ask the question well if you want.
Okay, so maybe the questions are going to come later during the tutorial. So let's move to the next one, which is this one. So this is the still the flow in a tube bundle, but now we are going to use advanced turbulence modeling for it. So this technique is called large eddy simulation. So the mesh is also going to be much bigger. It's going to have 3.5 million cells. It's going to be fully 3D. And the objective of this tutorial is for you to set up the whole case on the local or virtual machine. So that's explained in the tutorial. And then when you're ready, to copy file across on Archer, and then use a submission script to submit a job on ARCHER2. So yeah, I mix up Archer and ARCHER2, but it should be ARCHER2 all the time. And so to submit the job on ARCHER2, and then the simulation should run for about 10 to 11 hours overnight. And tomorrow you're going to post-process these results. So I think it's time for you to have a look at this one.
Okay, it seems like there's only 2 people that haven't been able to get the SSH key. For the rest, there's a step that you need to do after you generate that key and you log in first to Archer. So I'm going to show you what you need to do. You can do that now, or you can do that whenever you are in the tutorial logging into Archer. I'm going to share my screen so you can see what you need to do. So when you're in a terminal, whatever it's the terminal you're working on, whether it's the virtual machine or your own local machine, once you have uploaded the SSH key, you need to log in with username. That was the one that you set up when you create the safe account. And the name of the machine, which is ARCHER2. And you should be able to see that. If anyone has a problem doing that, please let us know as soon as possible, because there might be an issue with your authentication. So before you can do anything, you're going to need to copy a file that will set up your account the first time. This only needs to be done one time. Okay, so what you need to do is copy from work and our group for this tutorial, which is TA019. And then you're gonna find here a file called bash rc. Okay, this is a shell file that will set up your environment so that you can run Saturn correctly in Archer. So the first time that you log in, you just copy that into your home directory and rename it as .bashrc. Okay. So this instruction will copy the file that we have for you. You will also should have access to this shared directory because you're all part of the same group in your home directory. Okay. Once you've done that, you can just source the same file. And after that, you should have the command Code Saturne available for you. Okay, so this only needs to be done the first time that you log in. So I'm gonna list those two commands, that one and that one there. And if you have any problems, let me know. Okay, just to explain a little bit of what's going on, because there's a bit of confusion. The bashrc file that I gave you, that you copied, creates a link in your home directory to your work directory, so that you don't have to put the whole path every time that you want to copy things from your local machine to the remote machine. So once you source the file, you should have this link here in your home, which is, if you look at that, it's pointing to, this is my username obviously, but for each one of you will be your different username. So this path is equivalent to what just Charles put in the chat, which is home. So if I do this, you will see the same as if I do the full path that would be that. So they are both the same. It's just that when you source the bashrc file, it creates this link so that when you'll see later when you have to copy the mesh and you have to copy your subroutines and you have to copy your XML file, you don't have to put a very long path. It's just short. Okay.
Yeah, it's just that the work link, it points to the project C01 instead of TA019, and that's why it didn't let me access it. I don't know if it was created before or something, but that's the problem.
Okay, let me check.
I'll change this in the bashrc.
I think my bachelor is this. Maybe not. Ah, yes. Sorry. Yeah, you're right. This should be.
Hey, can you just log out or log in again? I just changed it. One. I just changed it.
Okay.
So can you log out and log in again to Archer?
Yeah, I'll
Me?
do that.
But you need to copy it again and source it again.
Okay.
Yes.
I don't. You might need to remove the existing link actually, because if I do this, if you had, yeah, it's better if you do that before you do that. No, that's wrong.
Hmm?
That's wrong.
No.
That's wrong.
Do it again. Do it again. Just delete. No. Are you which? Can you? Yeah.
No.
Yes, it works now. Thanks.
Yep.
Okay. It happens that for the course, I had to prepare for another account. So this C01 account for other people. So when I copied the bash RC, I missed that bit.
Okay, just to clarify, if you're in your home directory, when you log in to Archer, if you type ls-la like this, you should see the link for your work directory, and it should have TA019. If it has 0 C01 or C03, that's wrong. So if it doesn't have TA019, you should remove that link, then copy the bashrc file again, and then source it again. Okay. And for Ashish, what we're doing is copying from the local machine into the remote machine after you've created a case. So you copy the mesh file and the XML file, but there shouldn't be any subroutines. I see. I think you might be confused with the run and the actual creation of the case. So when you do the initialize, it's not really running yet. It's after you submit the case that it starts to run. So when you do this bit, it goes really fast. But when you do this bit, it just stays there until it. And this is related to what I was saying before, that in Code Saturne everything is separated. So what you do when you initialize is create the directory where it's going to run, is reading the mesh file, is creating that intermediate file between the preprocessor and the kernel, and is letting everything there ready for running when you're submitting. So it's because here in Archer you don't have a graphical interface that would do that for you. You have to do it in these two stages.
And to add on what Juan said, this first part, the run initialize, is run serial, you know.
Okay, so I can see that people have started submitting the jobs. You can check whether your job is working. If you go into your working directory and you type sq, you should see something like this. And the key thing here is the R, which means running. Okay, and it tells you which node is running, for how long, etc. But at the same time, while this is running, it's also writing this run solver.log file or listing file, which is the same thing. You can always check what's being written there. So this is the kind of information that you will get at each time step. Well, we're writing here every 25 time steps, but you'll have for each variable the number of iterations, the residuals, the minimum, maximum, etc. Right. So for all those that have the job running, now the only thing left is to wait. So it should run for about 10 hours. And the idea is that we come back tomorrow and we'll the results. I would encourage you to wait until you start seeing that the job is running. So if you type, for example, this timer statistics is collecting statistics for each iteration. So the first column is the number of iterations. So after you start, you see that it's actually running and it's doing some iterations. It means that everything should be okay, and you can happily go get yourself a cup of tea. In your execution directory, so in my case is this date, but you should have your own. There's a file called statistics.csv, this one. So that gives you every iteration, the total time seconds that it took, and it splits it into all of these different stages of the iteration. So as you can see, mesh pre-processing is only done at the first iteration, and then 0. And the same for the checkpoint and restart, that's going to be done every 50 iterations or something. Another good way to check that everything is running okay is looking at these two files, les.gui.e and .o, and then this number is going to be the number of the job. And that has the output and the error of what you would normally see in your terminal graphical interface. So if I show you mine, the problem is, I'll show you here. Problem is that there's two things. When you do the initialize, this instruction, can you see it? Maybe I should make it bigger. Here, this is the name of the data file that you copied from your GUI in your local machine. Okay?
Yeah.
But then when you submit the job with this command here, Saturne GNU, this job name should be alias without the underscore and without the. So, I mean, for some reason, that wasn't what you had, but I don't know if it was because you submitted this one or
yeah, I submitted the alias, but the XML thing, literally on the job name, I put that down as the XML thing. So
so it probably means that it overwrote this file because what that command does is create this file. That name that you put is a different file. So you need both. You need the XML file and this new name file. So if you put the .xml file in the submission script, it means that you overwrote the XML file. So if you look at your XML file, it should have all of these XML tags and stuff, whereas the other one should have like shell commands. Did you do another initialize?
yeah.
After you cancel the job? Okay, that should work.
And yeah, I've got the statistics as per your the one that you displayed. So I've got the stuff coming up, so that's not too bad.
Okay, excellent.
Yeah.
Good.
I'll leave the floor to Zhang then. Sorry. Apologies. Right.
Okay.
So do we just log off, or are we okay? Or
Yeah. You're done for today. Unless you have any
Thanks,
other questions.
guys.
Tomorrow.
Yeah, thank you. I'll talk tomorrow, and in that case, that's great.
Okay. Cheers. Bye-bye.
As William is asking, so is there anybody else having issues, or is everything going smoothly? Okay, so I mean, what I think is what you did when you created the XML file on the local machine, you basically went to look for a mesh which was not set or written or under the MESH directory. You got it from somewhere else. So basically, when you created the study on Archer, you have to have exactly the same structure. So in the XML file somewhere, I think the name of the mesh doesn't correspond to the road bundle and .gz, but it has got the full the global path. That's what I think is happening.
Yes, so can we manually override the path in the XML file?
Well, if you give me a second, I try to find which keyword correspond to the mesh in the XML file, and I just send you the link. I mean, I just send you what to do. Okay.
Yeah,
So
right.
you could
Thank you very much.
You could go to ARCHER2 under data, edit this XML file, and there's just something to change, but I need to find the exact syntax, okay?
Yes, all right. Thanks a lot.
Okay, can you edit your XML file and on Archer2, sorry, in the data directory?
I just found it. The path is stated to be the same, /home and so on. I need to change it.
So okay, so mesh space name that gives you /home and everything.
Yes. So basically, I'll change it to my work directory.
No. You just delete everything apart from the name of the file. Okay? You just delete /home and everything, and you just keep road bundle staggered on everything. Okay? So basically, I just added it in the chat. Okay?
Yes. Okay.
So it should look like this, because when the code initializes the whole simulation, basically he knows that this file should be in the capital MESH directory. In your case, I mean, you could have, I mean, a way to do what you have done is that to add a symbolic link in that MESH directory if you didn't want to copy it. Okay?
Okay, I understand.
Yeah.
All right. Thanks a lot.
Yeah, just give it a try and we see if it works first. Thanks.